Hey guys, good morning. Yeah. So I'll talk about machine learning. The promise and all that was just to get the CFP accepted, so don't expect too much. Anyway, so I started with machine learning about 6 months to a year back, and this world amazes me with how much stuff you can do and how awesome it is. So at the end of this talk, I just wanted to get excited about that too and go and try it out. You can read more about me there. Don't want to talk about that. The slides and the code that I'll show are up on GitHub and slides and all that. So I was preparing this thing, and then Tejas yesterday, everybody knows Tejas here, right? He had a couple of jokes that were exactly what I had, and I was like, oh God, I have to prepare new jokes now. But at night I couldn't, so it was too late anyway. So I didn't, so my jokes are still lame, but still laugh like you did for his talk, right? First of all, Happy New Year. Has anybody ever had 200 people shout Happy New Year to you at the same time? No? Want to try that? Yes. All right, so on a count of 3, right? 1, 2, 3. Happy New Year! That was actually much better than what I expected because I had 2 more steps after this. I'll just do one of them anyway. Let's try even better, right? Let the hotel know that we're doing something awesome in here. So, shout Happy New Year and stomp your feet. Don't worry, the floor is pretty strong, except probably this part. So, all right, like this. 3 times, all right? So, 1, 2, 3. Happy New Year! All right. You guys were already awake, I know, but anyway. So, we'll take a very brief look at machine learning. And there are many awesome talks that tell you what machine learning can do. This is not what this talk will do. I'll specifically focus on classification, which is one type of machine learning, and an algorithm that you can use to do that, which is SVM. And then at the end, we'll see how you can do this in Ruby. So yeah, this is my first talk, and I thought I should do a live demo, right? Before we actually go there. So what we're trying to do today is we have all these large data set of about 60,000 images that look like that 6 and 5 and 7. Each one is 28 by 28 pixels, and what we have is raw grayscale intensity. So you have 0 to 255. And there's this data set available that you can use to practice your algorithm on, or train your algorithm on. So it's hard to read, it's all binary, and I don't understand binary. So I put it out in CSV like this. And as you can see, most of the pixels here at the top, bottom, sides, they're all going to be 0. And in the middle, you'll see some numbers that's going to range between 0 and 255. So what we're trying to do is take these 60,000 images, basically have an algorithm learn those images, and then when we give it a new input, like another image that sort of looks like one of these, or maybe a little dissimilar, it should be able to tell us what it is, right? So that the MNIST set also comes with 10,000 things for testing. So first we'll run it through that and see what our accuracy is, and then I'll show you some of my bad handwriting. All right, so we'll talk about most of these things later, but I am basically, you don't need to know what linear is. I'm just showing that I'm doing it on 60,000 samples. And I won't do the all 10,000 right now. I'll just do 500 of them. And that's going to come back and say, hey, I'm 85% accuracy. And I didn't train the algorithm right now because that takes a lot of time. I already have it saved. And you can see the code and all that, the saved models in GitHub. But for now, the main important parts are this algorithm, it says is 85% accurate on the 500 samples that we tested. And all these things that you see, like for example, this guy, we got 2 images that are actually 9, but are reported as 0. All right, so those are bad. Everything that you see along the diagonal are good. Everything else is bad. And I didn't tune the algorithm at all because I want to keep it simplistic and all that, but you could do a lot more stuff. And SVM, I think it has been shown that it can get about 93% accuracy with this. All right, so another thing is, so I wrote down some of these numbers on a sticky note. That's probably not visible because it's all white. I'll see here. right? So something like this, right? I wrote it on a sticky and then scanned it in grayscale, and I'm trying to going to read it from my own handwriting. And so I did some of this image magic stuff. Who's familiar with image magic? Right, so I did some of that stuff to get the raw grayscale intensity out of that. And so I make my picture look a little bit like one of those things, right? So yeah, I'm going to use this guy. Let's say 0 is pretty easy to identify because not many shapes are like that. So let's see if it does the right thing. And it says, yeah, it says 0. That's good. And I've already practiced this, so I know which ones are working, which ones are not. One is working, and some of it are not working. And for example, I'll show you a 3. Look at how that shape looks, this guy, and then look at 9. The way I write 9 is very similar to 3, except this part, right? So I'm going to try 9, and it's going to tell me that it's a 3, right? So that's where you need more accuracy. You need to train your algorithm. Right? Anyway, I hope you sort of got a sense of what you can do with machine learning. So what we are doing here is, we are not explicitly programming any algorithm. We're just giving it a lot of data, and it automatically figures out how to solve the problem, given unknown data. Which is, I thought, amazing when I learned it. And it's basically statistics-driven algorithms to find patterns in data. So there are 2 types of machine learning algorithms. The more widely known ones are probably supervised learning, where you have lots of data. For example, let's say you're doing house pricing, right? You have the area square feet, you know the location of the house, you know how many bedrooms it has, is it an apartment, does it have a swimming pool, things like that. These are all attributes of our problem. When you know these attributes, you can basically, and you have some set of data where you know the prices, you can now feed it to an algorithm. And when you have unknown, like HSR layout, 2-bedroom apartment, 1200 square feet, what should be the price? It can tell you the price, right? Of course, that will need a lot of work, but that's essentially what supervised learning is. You are given some known data and then you predict unknown data. Unsupervised is, on the other hand, there's no classified data or something like that. You're just given a lot of data and you're trying to find patterns in that. And for example, recommendation engines like Amazon or even Flipkart's, everybody's recommendation engines, right? They would use something like that. The Flipkart guys will know better, but I'm guessing. And then you find groups or circles within your social network, things like that can be done with that. So today we'll just talk about classification. And so that example I talked about, house price, right? Let's say I have only one attribute. I'm going to keep it very simple here. And can everybody see this side, or should I be pointing at that side also? This side is fine. That side? Alright. Okay, so just one attribute we are focusing on, and I'm plotting all these houses. So this much area, this is the price. This much area, this is the price. Sort of something like that, right? And this is not exactly linear because there are other attributes. We are just considering one attribute. And you have this red dot here that you want to predict the price of. What do you think is the best way to do that?
Extrapolation.
Right, extrapolation. So this is a linear extrapolation, and I'm doing a linear thing because I showed you linear data. Your dots could be here, 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 and then in that case you would need a polynomial fitting curve. In this case, it's a linear curve. And then once you do that, you figure out the red dot is probably lies somewhere here, so you predict a price of about here, which is not bad actually, given this much sensitivity. So how do you actually solve this problem? How do you find the slope and all that on the line? The thing you do, before I show you the math, for every one of these points, you say that if I knew what the slope was, how would I compare it to this? So that's called the hypothesis, right? Hypothesis of every dot is going to be this line equation here. You probably know this is B and this is M, right? B plus Mx. But I'll call it theta 0 and theta 1 because you can have more than one attribute. We are showing just one. So that way you can do theta 1, theta 2, theta 3, blah, 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 blah. So you calculate the hypothesis, and right now you don't know theta 0 and theta 1. right? So you know the y value, which is the actual price. So you take the y and you find the difference between the hypothesis and the y while not knowing the hypothesis, right? So you're just forming the formula, and then you're trying to minimize that for the whole picture, right? So what you do is you take the h theta for every point, you take the y out, square it because then it's absolute, and then you find the sum of it. And this is your minimization problem. How many have heard about linear programming or optimization, minimization? Yeah, so this is basically a minimization problem. At the end of this, it will figure out what theta 0 and theta 1 are. And this was a linear thing, so linear, but it will have polynomial curves. Next up is, that was linear, so price is a real number, so you're trying to predict the exact price. Whereas this guy, you're saying, is this email spam or not spam? And this is a very famous machine learning thing that Gmail, Gmail started. So I'm going to keep it simple again. I'm just considering two attributes of an email: length of the email and does it have a dollar symbol in it, right? So based on those two attributes, I have plotted out, let's say, some examples. The red stars are spam emails, the blue ones are non-spam emails. Now, how do you, given an unknown email, how do you classify whether it's a red star or not? It's very similar to the previous problem. You're again going to find a curve that sort of is the difference between the red stars and not. And this one I made it a little confusing by putting some of these here, which goes to show that this is probably not exactly a linear solution. You need better, but anyway, for now. So like the previous one, we'll again create a hypothesis. This time we need the hypothesis to be between 0 and 1. So 0 means either spam or not spam, doesn't matter what it means, as long as we're consistent. So the y value is only 0 or 1, so your hypothesis is also 0 or 1. And this is a very famous sigmoid function that I will leave it up to you how to figure it out, but this only results between 0 and 1. And here, like the previous one, we were just using theta 0 plus theta 1 into h1, right? This time, that whole thing is the z here. And then you solve and minimize that equation again, you find theta 0, theta 1, and then you find what your y value should be. So it will come somewhere between 0 and 1, and you take the closer one. That's how you classify it, right? And how you exactly minimize those problems is, SVM is a powerful way to do that. Along with neural networks, it's probably the most widely used machine learning algorithm right now. It's called the large margin classifier, and the full form stands for support vector machine. We'll see what all those means. When I started, I had, why are these things called the way they are? Anyway, so again, red stars and green squares, and we want to segregate them. We want to find the line that divides them. We can think of many lines. There's a pink line here, there's a light blue line here, and then there's a deep blue line here. So what SVM does is it finds all the lines that it potentially can use, finds the critical points that matters as the distance between the line and that group, right? So in case of the pink one, this is the closest one for this side, and there's probably, maybe I didn't draw it. So one of these points is the closest one to the pink, or this one is the closest. So this, the closest one, is called the support vector for that group. Right? All these other points, when you consider the pink line, all those other points don't matter because that is your distance from that group. So it finds out the line that best segregates these things. And this is the support vector, and this is the margin. The length of that is the margin, hence large margin classifier. Alright? So that's SVM. We won't look at exactly the algorithm behind it. I know you guys are already there. So, and if you're feeling like that, it's okay, because this is about 6 months of time where I understood all this. So, but I know all you love coding, so we'll go down and get coding. Right, so before we start coding, one more small theoretical segue. We learned how to do 0 or 1, only 2 classes, right? Spam or not spam. How do you do when there are multiple classes? So in our example, we have 10 classes, the numbers 0 to 9, and we need to find out which number is it, right? What you do in this case is, we have 3 classes here. First,
we'll create three classification problems. First one is whether it's a red star or not. That's going to give you a line like this, right? It's a red star or not. And then we'll do another one that's a blue circle or not. And then a third one, whether it's a green square or not. Then anytime you have an unknown input, you ask all these three things, what do you think? So they'll say, I think it's a red star or not. And then similarly for the other two. You will also remember, it will also give you a number, right, between 0 and 1. So you take the one that is the most confident about its answer. So if you get 0.9 from the red versus like 0.4 or 0.3 from the others, then you would take that it's a red star. Right? So that's multi-class. And right, so we'll get down to Ruby now, which is what you guys all love. There is a very famous library called libsvm, which is available on any Linux, and there's a gem called Ruby libsvm. We'll show how the code works with that, and that's what the code that I showed on GitHub is actually using that. We'll also talk about Weka, which is some Java library. Don't hate it because it's just Java, and it's awesome. I'll show you how to use that from Ruby. And you could, of course, so all we're doing here is matrix or linear algebra. So you could do all this yourself. You could find out the eigenvector from the matrices and figure it out yourself, but don't try to do that because it's very complicated. Right? And there's, who has heard of Apache Mahout? That's probably very, very well known because it's highly scalable, but it involves setting up like a Hadoop file system and all that, so I'm not going to take all that today. Right, so using libsvm, and the exact code is in this model file since we're still using Rails, right? So then you create a problem, and then you create a parameter. And the parameter means things like whether you're using a linear kernel. The shape of that line is called a kernel, to put it simply. So whether you're using a linear kernel or a polynomial one or something like that, you'll fit all that. As you can see, I'm just doing this most simple thing, which is taking the defaults. And then our examples, as I showed you, is 60,000 images. So it's an array of 60,000 items, where every item is again at 28 into 28, so 784 numbers, where every number is between 0 and 255, right? So you wrap all that up in a libsvm node, feed it into the problem and as labels and features. Features are these guys, labels are the known labels, like is it a 1, is it a 2, things like that. And then you train your algorithm. The training takes some time, so usually you would save it to a persistent and then read that back later on. And then use that to predict when you given new data, like for example, my own handwriting, you take the array of 28 by 28 pixels and you create predict it based on what it is. Right? Simple stuff. Right. Weka is another awesome tool. It's from a university in New Zealand whose name I cannot pronounce well. It goes something like Waikato. I don't get it. Anyway, so another library. So instead of showing you the screenshots, I'll just show you Weka. Weka is awesome because it is so versatile that it comes with a GUI as well as a Java API. And I'll just show you the GUI part. So this is my training data, right? It reads something called ARFF, but it can read CSV also. And I already read it in here. And it lets you picture like how your data looks like, first of all. So you can see I read 4,784 images from that file. And it's pretty evenly distributed among the different classes of numbers, right? And I ran it through something called normalize. So that's a step where, so my numbers, attributes go from 0 to 255. That's good, but think about having your house pricing problem where your one attribute, which is square feet area, is 1800 at the scale of thousands, and another attribute, rooms, is at the scale of 1 or 2 or 5, right? So you would need to normalize it so every attribute is between a certain scale. And Weka expects that from any algorithm, so I just did it that way. And you can see these are all my 784 attributes here. And I'll just show you something in the middle. So you can see max is 0, min is 0, max is 1, and like how many distinct values and all that. the most awesome part, and I'm going to say this multiple times, the most awesome part of it is you choose any algorithm you want, right? So you can do a bias. Some of you may have heard these names like a random forest or neural networks and all that. You pick any one of them, and I picked libSVM, which is the SVM. And I'm saying I'm going to use 90% of the 5,000 instances to train it, and the rest 10% to test it out. And then it's going to build the model, and then it's going to also save the model and all that if you want. But it will probably take about 7 to 8 seconds, yes, 6 seconds. And then now it's testing on those instances, and soon we'll report what the accuracy was. Yeah. So this is probably not readable from the back, but I didn't build this software, so I don't feel bad about that. 91% accuracy using SVM. Okay. And then this is the confusion matrix. We already saw that. Almost everything is along the diagonal, so that's good. And this is the third best thing about Weka. It comes with something called the experimenter, where you can feed it the data that you have, and you can have multiple algorithms or the same algorithm with different parameters, and it's going to compare all this and tell you which is the best algorithm for you to use. Right? So this is really, really awesome stuff. Use this more. It comes with a Java API, and this is how you use it. So yesterday they just told you how the best way to write Python. The best way to write Java is also in JRuby actually. So a class like this, Weka.classifier something, becomes a Ruby module, and methods with camel cases become this. And I'm so used to writing that way that I hate doing camel cases anymore. So yeah, this is awesome for me. So this is the only way I write Java and show it now. So yeah, you're setting the options like linear kernel and all those coefficients. You're building it, you can save it, and then anytime you have new data, you classify it. Right? And then we didn't really touch upon what we didn't do today, and there's a lot of stuff. This is just like the tip of the iceberg, even less than that probably. There's something called regularization, where if you have lots of points, like almost spread over, and you like your algorithm is naive enough, it's going to create a curve that goes through every training example. So when you have a problem where your data is very similar to the training example, it's going to predict exactly accurately. Whenever it's like here or there, it's going to be completely wrong. So you need something called regularization to prevent that. It's mathematically very easy. We talked about normalization, we talked about polynomial classification. And I also did another thing which is sort of important. So we have 784 attributes in our problem, and it's pretty time consuming to like create the model test and all that along with that, given 60,000 elements. So you do something called principal component analysis, which figures out which are the important attributes out of this. Because if you remember the image, the top, bottom, and the sides are all 0, right? Almost always. So those are really not important to figure out. And data generation. And so we'll talk about that today. And then, if you're already inspired, go ahead and take this class. This is where I started. The machine learning Coursera class. This is the first Coursera class. Pretty awesome. And it goes very deep. So that's good. And then the collective intelligence book is really good. Then there's this website called Kaggle. And you can, when you're picking up this stuff, they have something called competitions, and people like companies actually post their machine learning problems here, right? And if you solve it, then you get like, that much money. That is the top amount, but there are lots of free competitions as well, where you can test out. So this is one of those, the digit recognizer is one of those, and you don't get any money for that, yeah. So that's pretty awesome, you can try it out with that. And that's it. Thank you.
We have time for questions. I want to go first. So in the case of when you are learning from existing data, are there any well-known strategies for handling conflict? For example,
strategies for
handling conflicts. Basically, two sets of data. They have like very matching parameters, but like only few of them differ drastically. For example, if we take the example of the pricing of the flats,
Right.
So neighbors in the same society on the same floor, and they are probably offering their flats at drastically different prices.
Okay.
So in such cases, are there any well-known strategies to handle conflicts?
So basically, what you're saying is your data is sort of intermixed,
The intermix.
right? That's probably not going to happen in a real world, or you probably have not found the right attributes. Because why is your neighbor giving the flat for a place,
Yes,
right? So that needs to be one of your attributes as well, right? But if they're really like well segregated, then so what I showed was just the linear curve. You can have lots of polynomial, and by polynomial I mean weird shapes. So you could have like the center is that part, and again the outside part is falls under 1 plus, whereas the middle part does not. Things like that. So it's basically you have to try out a lot of things, basically to figure out what is the algorithm that you need.
Yeah. Can you do the same pattern on any other media other than the data? Like we're having like textual data, right? It's something like numbers which are storing into it. There is something like voice recognition kind of thing. How does it work?
So the same way here, like we showed, what we were working with were images, right? Image is ultimately just numbers, right? When it comes down to it. Similarly, for voice, you would either find the frequency or the amplitude, things like that, which I don't even remember right now, but you would find numeric comparisons of that voice. And actually one of the widely known uses of machine learning is filtering out speech from the noise in the background, right? So that what they do is you're trying to figure out my voice versus like if there's an aircraft going behind me, how do you get that out? So yeah, you can definitely do that.
It's like why you choose Ruby for it, because according to SLS talk, they were saying if the CPU intensive, then you have to go with a combined language instead of a different language, but it actually choose Ruby, and yeah.
Okay, so first of all, this is a Ruby conference, so that's one big reason. Second is when I'm using libstm like you saw, and that's at the C level, so it doesn't really matter what I'm using. If you're using Weka, I'm using JRuby. Right? So at that moment, it doesn't really matter. I would still say that most people who are doing machine learning are not using Ruby, to be fair, because even the reading of the data might take, because you're talking about gigabytes or terabytes of data, it might take a while. But my point here is, you guys all know Ruby or are interested in Ruby, and this is another thing that I want to introduce you to. So this is probably the best way to learn it, because if you're going to learn like Julia or R along with all this, you're probably going to be a little lost. So maybe this could be your first step. Try it with the language that you already know, then progress if you get really interested in this stuff. So progress on to what tools you would usually use.
Any more questions? So that's it then. Thank you, Anand.
Thank you.